So welcome back everyone to the third Encode times Harmony Educate series event. Today, we are very excited to be joined by a Harmony protocol engineer, Max Mustermann. I'll be throwing some important links here into chat, so feel free to check them out just regarding Encode Club, Discord and Twitter, as well as just a reminder that this Educate series kind of predates a upcoming hackathon that begins on the 27th of September. So if you have any interest in building on Harmony or any projects in mind, feel free to kind of check out the hackathon as well as some of the upcoming Educate series events that we have. Also throw my kind of Twitter and email into chat too. So if you do want to reach out, any questions about the series or about the upcoming hackathon, feel free to reach out to there as well. And just a reminder, in the Encode Discord invite that I will be sending out, there's a dedicated Harmony Educate as well as Harmony hackathon page in there. So if you want to connect with other developers or students that are in the kind of cohorts, you're more than welcome to do that as well. But without further ado, if any questions do come up throughout this presentation, please do throw them in there in chat, and we'll be sure to get them answered before the session ends. So Max, without further ado, feel free to take it away.
Hey guys, how are you doing? I'll get started. As you guys know, Harmony is an EVM compatible chain. I'll start with an introduction of the basics, how it's sharded and how sharding works, how the staking works at Harmony, and what is the consensus algorithm that we follow. Lastly, I'll talk about the randomness generation that occurs on chain. So, broad introduction, I'm sure you've seen this in the last Harmony session. We have 4 shards, 1,000 validator slots. The block time is 2 seconds and the finality is exactly 2 seconds because consensus guarantees that it will be final immediately. It is compatible with EVM, so all of your toolings that work on Solidity, all of your Web3 Pi, Web3.js, everything works directly. There is no extra changes required. In terms of randomness, we have an on-chain randomness oracle. It serves other purposes in the consensus as well, which I will describe. And because it's sharded, we have low transaction fees of less than 1 cent. Talking about sharding, how sharding works is that state is shared across shards. I mean, state is independent of the shard that you're in. So somebody who wants to run a node or wants to track transactions happening on one shard does not need to store the information from another shard. This helps save costs and increases throughput while reducing network congestion. Each shard runs independently, and while there is the beacon chain is relied upon for committee election and reward distribution. I will talk about committee election and reward distribution in the consensus section. So, like I said, the network is validated by a committee of validators, and these validators are chosen based on the stake that they have made, and that this includes the stake that is delegated to them. Transactions are processed separately by each shard based on the shard ID that is specified in the transaction. So there are 2 types of accounts. One is the user-owned account and one is the contract account. Some of you may call a user-owned account as an externally owned address. Each account is identified with a PEC32 address in this format. Since we are Ethereum compatible, we also have the equivalent OX addresses. User-owned accounts can have balances on one shard or multiple shards. You can see it in the screenshot. And smart contracts can be deployed across different shards. So you can have a smart contract on shard 1, you can have a smart contract on shard 0. And these smart contracts, while they may have the same underlying code, they will A, have a different address, and B, they will have an independent state. Since they have an independent state, like I said, the storage costs for smart contracts that are a key part of any blockchain are spread out across 4 shards. Now, how do sharded transactions work? Whenever somebody sends a transaction, they have to send a shard ID along with it. This shard ID, if it lands at the correct shard, if the transaction lands at the correct shard, it will be processed by the shard. However, if the shard ID does not match the shard to which it is sent, the transaction will be rejected. And to maintain Ethereum compatibility, what we've built out is that transactions that do not have a shard ID will be processed immediately by the shard, if they can be processed, provided the chain ID matches. And there are cross-shard transactions as well. You can send native tokens, that is Harmony 1 tokens, from one shard to another. All you need is to specify the to shard ID and the from shard ID, which are already specified. These transactions are eventually atomic, and there is a 2-block time latency. So if somebody makes a transaction on shard 0 that transfers, let's say, 100 ones from shard 0 to shard 1, the moment the transaction is processed by shard 0, it is likely to be processed by shard 1 immediately after. And once this happens, it happens in an atomic manner. The moment the balance goes out from shard 0, it will reach shard 1. And I'll talk about staking. I'm sure all of you who've been in the cryptocurrency space know how staking works. But broadly, I'll try to explain how specifically that on Harmony works, and it's not a very different model. Stake is delegated to validators, and validators are responsible for block production and block validation. We have about 43% of the ones in circulation currently staked. And we have a annual reward of 441 million ones. So it translates to a yield of 8 to 12% for stakers. Here I have pasted a screenshot from staking.harmony.1, which describes a validator's performance. There is the uptime, the slots, which I will explain. It says that they have 1 slot on shard 0. The lifetime rewards that they have earned in 1 is roughly 365,000 ones. And the latest expected return is 9.84%. So like I said, within the 8 to 12% reach. Now talking about validators. So in any proof of stake blockchain, validators are responsible for the security of the chain. They stake in some balance, some native tokens, that is ones, on the chain. And they say, this is my stake. If I misbehave, you can slash it. And that's an incentive model for them not to misbehave. And people who trust these validators can delegate to them. So the validators receive the block reward for running these nodes, doing their validations, and a commission from the delegator reward. This commission is supposed to be at least 5% of the delegator reward, although to help bootstrap newer validators for a couple of periods, it can be less than that. Slashing occurs when validators double sign. So double signing in this sense is not a double spend, as you may be aware of in proof of work blockchains. Double signing here means that they sign two different messages for the same block number. So let's say somebody is producing block 5,000 and using the same private key across two different nodes. They sign one block 5,000 with 10 transactions, and the other node signs one block 5,000 with 11 transactions. So this leads to a mini fork in the chain. And this is called double signing, and it is a consensus violation. In this case, they will get slashed. In slashing, what happens is that half of their stake is burned, and the other half is sent to the current leader. The current leader is so whenever the slashing event is reported and it is validated and included in a block, you go back in time and find the stake that they had at the time of the violation, the consensus violation, and you slash that stake. So the person who includes, the validator who includes this report in the current leader, in the current block, is the leader, and they are given 50% of the stake. You might know that Ethereum has slashing for downtime. if you don't sign blocks, you will get slashed. We followed a more freer approach. We do not want to slash validators for downtime, but we do not accrue any rewards to them. Secondly, if downtime is measured, let's say downtime is measured as the number of blocks that the validator actually signed divided by the number of the blocks that the validator was asked to sign. So if this number falls less than 2/3, the validator is ineligible for re-election in the next committee. And if there is a certain validator who figures out they had an issue with their setup that made them ineligible, and now they've remedied the situation, they can send a transaction that marks them active on the blockchain. If they do this, they are now again eligible. Okay, now talking about, one sec. Now talking about validator slots. So we have, like I said, 1,000 validator seats on which validators can bid to be elected. So how it works is that there are 1,000 seats. Each validator shows up and says, this is my stake, this is my stake, this is my stake. This stake includes the self stake and the delegated stake. So you get the total validator stake, or the total delegation, as we call it in the code base. You sort them in a decreasing order. And the first validator gets the first seat, the second validator gets the second seat. And that's how it's done across 1,000 seats. But let me move to the next slide. This is what it will explain. But how it works is that the stake, the effective stake, is capped within a range. So let's say we have the median stake of 100. In this slide, you can see that within 115 and 85 is the bound range of the stake. So let's say there is a validator which has a stake of 200. The effective stake for this validator will be exactly 115. Now, if there is a validator that has a stake of 60, the effective stake for this validator will become 85. This means that validators should optimize their stake to be within this range. How do they do that? So a validator can divide all of its total stake into multiple slots and bid using that stake per slot for each slot. So we'll go back onto the previous page. So validators choose the number of slots to bid for with the aim to maximize probability of election. So if you, let's say, have 10 slots and your total stake is 1,000, the stake per slot becomes 100. And with this 100 stake, you will be able to bid for 10 seats or 10 slots. I'm using seats and slots interchangeably, but you'll be able to bid for 10 seats. You want to be in a range where you're close to the median, so that you're elected across those 10 seats. This way, we're able to avoid stake centralization per slot, and a single shard attack is, the probability of a single shard attack is reduced. And okay, moving on. And I'll talk about how our consensus algorithm works. In this case, we have, so if you can see this. So we have a leader which proposes a block header. It broadcasts the block header to the validators and the block in an optimized manner. The optimization is a bit complicated to describe, but it works by breaking it into pieces and sending it to different validators who will then aggregate it. But anyway, you broadcast the block header to all of the validators. So from the leader, the block header reaches to all of these validators. They will verify this block header. If they verify it and consider it to be valid, they can sign it. Once it is signed, they are supposed to send the signature back to the leader. So in a couple of blockchains, what happens is that all of these signatures, all of these block headers, they are broadcasted to everyone in the space. But in our case, what happens is that we're only broadcasting to the leader. So this avoids some network overhead, and we're able to make block time faster. And the leader is supposed to aggregate these signatures into one. And this is the announce phase. So the leader is announcing the block. The next is from here is the prepare phase, is when the validators check the header and sign it and send the signature back to the leader. Once the leader receives a certain proportion of the stake vote, the leader will aggregate these signatures here and rebroadcast them. In the commit phase, the validators ensure that the signing that was sent in the prepare phase is valid, and they verify the entire block. So right up till now, they had only verified the block header. Now they're going to verify the entire block. If they verify the block, including all of its transactions, all of its state root, they will sign it and again send it back to the leader. So this is called the commit phase. Once the leader receives enough votes, the leader will commit the block into its database, broadcast it to everyone, each validator, who will do the same, and then we move on to the next block. This is also explained more in depth in our white paper. You can, I'll just type out the link in a while for the white paper. It's so the key focus is that there are not multiple round trips, and that there is signature aggregation at the leader level. Okay, now I'll go back a couple of slides, and here I'll explain this graphic view. So let's say there are these many slots for validators, and this validator is bidding for 400 slots, this guy is bidding for 300, but this malicious guy is bidding for 200. And let's say they arrange their stake in such a manner that they are allocated, they arrange their number of slots in such a manner that they're allocated to one single shard. What will happen is that this malicious validator can then overtake the shard because they have the majority vote in that shard. To prevent that from happening, what we do is that we randomly assign the validator to shards. So instead of you getting the shards in those decreasing orders that I had specified previously, your probability of election is based on that decreasing order, but the slots that you will get will be random. And the first 200 slots, let's say, represent shard 0, the next 200 represent shard 1, the next 200 represent shard 2 and shard 3. So in this event, your allocation to a specific shard will be randomized. This prevents single shard takeovers by malicious validators. And for this randomness, we need a random number. And here I will describe how the random number is generated. So there is a pre-random image which is generated by each validator. Each validator will use the current block hash as an input and their own public key, and they will generate a randomness pre-image. All of these validators will send this randomness pre-image back to the leader. The leader then aggregates all of these pre-images, like the consensus algorithm that we just talked about. The leader will aggregate all of these pre-images into one combined pre-image. So if this random pre-image were the final random pre-image, the leader would have the possibility to influence certain transactions. Let's say there is a transaction that's a bet on using on-chain randomness, and the leader knows the random number. The leader could potentially influence this this transaction and not include them in this specific block. But what we do is that we have a verifiable delay function, which takes the verifiable random function as a pre-input, and it guarantees that from the pre-image to the actual random number, you cannot get until, let's say, k blocks have passed. So the leader doesn't have any room to be malicious. And since the leader cannot be malicious, the leader cannot alter the allocation of the nodes across shards. And these are the toolings that we have. We have the JS SDK, the Python SDK. So I maintain the Python SDK, and you can anytime message on Discord on the Harmony channels, and I generally am available to answer these questions. We have the CLI, which is the Go SDK. This one also I sometimes contribute to. The explorers and the wallets. So in terms of wallets, we have any wallet that works on Ethereum will definitely work on Harmony.
Hey, Max, yeah, thank you. Great overview of everything there. And Max, there's one question there in chat if you want to take a look at it.
Hey, Pranav. Yes, you can use smart contracts. Any Ethereum compatible tooling that you're already using can directly be used on Harmony. Just change the endpoints and you get some funds to pay for gas.
Great. Well, yes, so we will go ahead and wrap things up here. Just as another reminder, the next event of the Encode times Harmony Educate series is coming up next week on Tuesday on the 6th of September. So I'll go ahead and post the invite link here. And yeah, please do reach out with any questions just about the Educate series, about the hackathon, or just Harmony or Encode Club in general. And I'd be happy to help and kind of hopefully point you in the right direction. But without any other questions, Max, again, thank you so much for a great technical deep dive into all things Harmony related. Reminder to everyone else, we will be posting the slides recording onto YouTube and Medium here by tomorrow morning. So if you want to go and rewatch it or kind of share it with your friends, you're more than welcome to that as well. We'll put the link again on a YouTube and Medium and kind of share that with you all in the Discord channel. But yes, without anything else, Max, again, thank you. And to everyone else, thanks for showing up, and have a great rest of your evening, morning, afternoon, wherever you're located.